and we are basically finding that this is a very good material. Most of the OEM goes for it. The other material today also was from ArcelorMittal, advanced high strength steel. The first generation and the second generation. What is the difference between them? I explained to you that austenite is at room temperature. That is the basic of advanced high strength steel. What is available at 723 degrees centigrade or 950 degrees centigrade for other carbon constant, now that temperature is brought to the room temperature by adding manganese. Manganese plays a very important role here. And you can see the effect. The austenite being so good deformable material that one could practically go up to 100% deformation with this kind of steel. And extremely high strength. Means I am getting this. But just imagine who will deform this material. You will need such a big press to get that force because the strength is very high, the strain hardening is very high, and the elongation is very high. Your force increases exponentially. Practically, all OEM are having problems using this material because the press does not give that enough force to deform that material. One of the biggest reasons why this advanced high strength steel is not successful, because you cannot make a totally new press. Yes, you can do it, but it is enormous pressure required to deform this material. Otherwise, it is a very nice material. Plus, additional advantage happen is that this material can be used both for the absorption of shock, because it has a high tensile strength, plus absorption of the deformation. When you have advantage, you have some disadvantage also. And the biggest disadvantage is the hydrogen is there inside this material. And hydrogen embrittlement happens, and eventually with the time, this material start getting cracks because of hydrogen embrittlement. The second problem, basically, here it is happening that this material has a very, very high spring back. You can imagine that your spring back is dependent especially on the elastic energy stored in your body. And what is the formula of elastic energy? If I would be having this as your sigma y square upon 2e. This is elastic energy stored in your body. Sigma y is so high, elastic energy is so high, and that gets released when the part is finished. Practically impossible to control the geometry. Forget pull compensation. This part cannot be compensated. That is one of the reasons that this part is very difficult to form. The third problem is the welding of this part. When you do the welding of this part, basically you are creating martensitic there, because actually this part has a austenite structure. Now welding it, you are basically cooling it in that some area very fast, so you are creating some martensitic bend. It means that basically you are creating a ductile structure in between brittle structure. Now there is a crash. What will happen? That brittle structure will collapse. So basically the weldability is a problem. So three problems: spring back, weldability, hydrogen embrittlement. Part has no future. That's why I asked it whether it is possible to do anything. Up till now, in last 10 years, I've seen that everyone is trying to find the solutions, but we have no solution. Otherwise, it's a wonderful material. So let's skip towards our main thing, warm forming steel. This will at least rule for the next 20 years in the steel industries, or I would say automobile industries, because there is no option at present other than this. There are two main processes how we can do basically warm forming. Basically, warm forming can be done two ways. As that, first you have this part. You don't do warm forming. First you deform the part. Make it complex part, cut it, everything. It is a soft part. 300, 500, 350 I said. It is the yield strength. Very soft part. You can cut it, you can do it, everything. You can give complex shapes. Then you send it to oven. Make it into austenite. After that, you create again a small calibration process, a forming process, to see to it that the tolerance is within the tolerance accuracies. And then some surface finish like galvanizing. because now you can apply the zinc outside it, because you don't need to do before that, otherwise the zinc would evaporate, but now you can put the zinc coating. One way, direct method. No one uses it because it is very expensive. You need 2 times the part to press it. Who will do it? Everything in automobile comes in terms of cost, in terms of how fast I can make the parts, what is the economic benefit of this part. This has no benefit. When you do 2 times the handling of part, that part has no future. So now comes the second process, direct process. This is the most commonly used process in practically all automobile. You have the part, you put into the oven, go to 950 degrees centigrade. The part becomes complete austenite, very good deformable part. Now you put it into the forming and you form the part in the hot condition, but your tooling are cold. You are holding the part for some particular seconds, normally 6 to 10 seconds, based on the temperature of your tooling, and the part gets cooled, convert to martensite because the cooling rate is faster than the critical cooling rate, and finally you cut the part by either laser or with the tooling. Normally the laser is used for the cutting problem because the part becomes so hard that normally the tooling cutter does not work. I am giving you a more practical approach. People will see there are tooling cutters for that and these things. I have not seen it. People are using laser cutting. Now here the part can be treated further with zinc, but that is also additional cost. So what people are using is aluminum silicon coating before that, put it into the oven, deform it, aluminum silicon coating will remain. There is no zinc coating necessary after that part. So no zinc, no second forming, the part is feasible. And this part has extremely high strength, 1500 MPa, good deformation, direct method used by most of the OEM. So what we are doing it, we were here when the material was delivered around say 550. We go to the temperature, the material is very high deformable because of the temperature plus austenitic, and then we quench it and go up to here, very high strength. One more advantage we get it. You can see here the spring back problem. If you have double face material, you will have got high this spring back. If you have soft steel, that will be the second one. If you have this steel, no spring back. It's like a dead material. This material can never have a spring back because there's no elastic deformation stored in the part. Everything was plastic deformation from beginning. So I don't have to worry about the tool compensation. Believe me, it is one of the biggest cost advantage. When the spring back comes, you will have spent so much of time with that part, and if it is the spring back is changing all the time, it is a big headache. So OEM will prefer to go for double the cost if the part is having no spring back, because the spring back is a big issue. So basically, as I told you, we are going in austenite stage and we are cooling it here. The cooling is not done in the water. The cooling is done inside the tooling. What does it mean? I need to have a very fast cooling rate. It means I should have some kind of steel which should take the quantity heat very fast. So here we are using a different kind of steel with a very high thermal conductivity. Normally a company, Rovalma, has a type of steel which has double the conductivity compared to the normal tool steel. Plus, this tool steel have a water canals here inside it. It is very important that the water should flow so that heat should come out all the time. Otherwise, I will not get martensitic. I will get bainite structure. It is not that bad, but still I will not get that high strength which I want. So basically, if I'm thinking about how much time it takes, like I would say, first you go into the heating chamber. There are like, you must have seen the pizza oven. Put it here on the top. Similar, very similar ovens are there. You put the blanks, put the blanks in different vertical direction and take the blank out which is heated. Normally it takes around 8 to 10 seconds to heat the temperature to 950. That will be normally the oven type. Or one could also do induction heating, which is much faster. Then you have to take that part, put it into the machine, plus close the machine. We are not deforming it. 6 seconds. Then you are deforming the part and holding it for 6 seconds. Then during the 6 seconds, both deformation as well as cooling is taking place. And so we can say around 12 seconds is one part. Too much actually. When I talk of normal conventional steel, I talk of around 2 seconds per part. 12 seconds, too much, but at the same time added advantage. The normal strokes which you see in automobile are 25 to 30 strokes per minute. That is the productivity you need it. If you don't get that productivity, nothing is interesting. Everything comes to that productivity, comes to that cost. Mass production to the highest extent. But we have no other option because we have to increase the strength, increase the absorption. We have to give 12 seconds. It means there are a lot of machines in the parallel which are doing it to get that part. Now, it is possible that we may not need for the complete part the complete strength. If I take off the B-beam, normally my crash comes from the side, and this area, on the top area, needs to be much stronger. But this on the bottom area does not need to be stronger. In fact, it's better if it is soft. Then why am I actually doing it complete part hot, complete part martensitic? Can't I have something where this is a very good strength, this is very soft material? Yes, it is possible. We know this TTT curve. Back to TTT curve. If I follow this path, it is martensitic. If I follow this path, it is bayanite. If I follow still on the right, it will be pearlite. It means if I control the cooling rate, automatically I have a different kind of microstructure, I have a different kind of hardness. And this is exactly what we are doing it. This we call it as a soft zone technology. We are basically here, there are many ways of making this soft zone technology. First way is we are basically hitting the part uniformly to 950, but the cooling rate of this part is much slower. It means the flow of water is less. The different kind of steel is used, so the cooling rate is not that high. Automatically you will get the different microstructure. So one way is that. Other way is, why heat this part? Why heat it up to 950? Why give that only energy? Why only not heat that required other part only? So how do you put it? When you have this part, you put a big mass on that part, ceramic or any additional mass, so that the convection heat is not touching that area of part. So that area of the part may be just 200 to 300 degrees centigrade. It will not even reach austenite. If it does not reach austenite, it cannot become martensite. So second way is, don't heat the part, don't heat that required temperature. So basically, either by controlled heating or by controlled cooling, we can have a second advantage of this hot forming, and that is basically we create intentionally different strength at different areas. That's why when I talk about this lecture as a light metal, actually it is the wrong word. I would say material utilization